Hi everybody, welcome to my 10th torsional bar video. In this video I'm going to be solving the problem you see here. I'm going to be finding and plotting the internal torque in this torsional bar configuration. If you want to know something else about torsional bars, feel free to check out any of my other torsional bar videos. So the first step in finding anything that's an internal, in our case an internal torque, is going to be to expose that by making an cut. So I'll make a cut right here and put an arrow this way, and that's going to expose the internal torque in this section here, because this section can be described by one equation. I'm also going to make a cut here, but I won't label the arrows. We'll do that later. So let's get a free body diagram of this piece on the right. I'm going to call this section 2 and this 1. Alright, so free body diagram 2. Okay, so this is the free body diagram for the second piece. Now the first thing that we want to do is somehow replace this distributed load by a point load that we can place on this piece. Alright, now we'll go through the process of what that is, but first let's figure out which direction it's going to go. Is it going to point off to the right, or is it going to point off to the left? Now the way we do that is by looking at the direction of the curvature of these arrows. So this one, the arrows are curving out and then back in like this. So using our right hand rule, take our right hand, and the way that our fingers curl is the way that the torque goes, and our thumb points in the direction. So we're going to replace this with an equivalent system that looks like this. Okay, so this force has been condensed into this. And I'm going to call this little bit here T applied in section 2. Alright, so I'm just going to do a quick explanation on how to find this sort of distributed load. Because when I was studying this, I found it quite confusing actually how to wrap my mind around this. I mean, I can memorize a formula, but I always wanted to really understand it. Alright, and it's good that you tried to do that too. Not to sound too condescending, but that's just the best way to learn something. So we can draw this little piece here, and we can do some calculus or whatever, but let's just do a real simple example, and we'll use forces instead. So let's say we have a piece of bar or something. It's of length L, and it has a load intensity Q on there. Alright, so we're going to say that this is a force. Now how are we going to go about finding the total force that this distributed load applies? Well, we know that Q is going to be newtons per meter, right? So to get total newtons, we need to get rid of this meter, so we times it by the length, meters, and that gives us just newtons. So the total force is just going to be QL, right? Newtons per meter times number of meters. Now let's put this on an angle. Alright, you have no force here, and then it slowly works its way up to more force with Q there and L here. Now, what does this Q mean? Alright, here it meant newtons per meters. Here, it still means newtons per meters. Newtons per meter. In this case, Q only applies for this point at the very end though, because as soon as we move a little bit to the left, it's a different value. So now how are we going to find the total force? If we did F equals QL, newtons per meter, times meters, we'd actually be finding the force from this area here. That's not the case. We only have half of that. It's a triangle. Well, that's an easy fix. Divided by 2. The total force imparted by this triangle is QL by 2, or newtons per meter times meters. And then because of the geometry, we divide it by 2. Alright, it's the same case if we would have a distributed load that's applied, via some sort of quadratic function. like this, we still want to satisfy this, newtons per meter times meters. And here we could just newtons per meter times meter, boom, one whole section. Here we have to take that section and divide it by 2. Here we need to take this section and then divide it to an infinite amount of pieces and then add them up. So it's essentially going to be newtons per meter, something describing newtons per meter. So Q as a function of x, dx. So in this case, the dx is a small amount of length, that's the meters, and the Q as a function of x is going to provide us with newtons per meter. So if we take this first little dx segment, we have a certain amount of newtons per meter. We times it by meters. We add it to the next little section of newtons per meter times meter, which is a slightly greater amount, and so forth until we get to the end. So essentially what we're doing in this system is summing up an infinite amount of this system. Alright? So that's the way I think of it, as newtons per meter times meters. Alright? Now this is all forces. We're dealing with torques. So in torques, the only thing that changes is this piece right here. Instead of being newtons per meter, it's going to be newtons times meters per meter. Alright, so this is kind of confusing because you might cross this off, but I like to think of it as Newton meters per meter times meters. So everything I just said here applies the same, except for newtons per meter, it's just going to be Newton meters per meter. Alright, so it's not an applied force, it's an applied torque. Alright, so I hope that made some sense to you. Alright, it's very worthwhile to go through and understand why these equations are true. So here we knew what the force per length was. Here we don't know what the newtons times meters per meters is. We need to develop an equation that tells us the newton meters per meters at any point depending on where we cut. Alright, so let's do that by pulling this little bit off here and drawing a bigger piece. Alright, so this is actually part of a larger distribution, and the end magnitude of this we're giving is T by 3L. Okay, so at this point, T by 3L describes how many newton meters per meters are at the very end. Okay, and then here we're going to call this arbitrary newton meters per meters. So how much torque per meters at this specific point, we're going to call that T. And then the total length here. So some people like to start to X at the origin and then say X applies between L by 2 and L. And other people like to say X starts here and say X is valid from 0 to L by 2. I'm one of those people. You can do it the other way too. That's probably better if you're going to go on to find the the amount of twist. But I like to measure my X from where the very outer region of my free body diagram is. Okay, so that means this distance here is X, and then this is L by 2 minus X. Alright, if you'd like to measure from the very base, this would just be L minus X. Okay, I like to do it this way. It's up to you. And then similar triangles tells us that T by L by 2 minus X equals this here, T by 3L divided by this total length here. Alright, and that is actually L by 2 if we're talking about the very outside piece. So you can rearrange this and say T is equal to 2T Alright, so this function, we can say it's a function of x, that describes how many newton meters per meters are being applied at any point along this line. So to find the total amount of newton meters on just this rectangle here, we're going to take this, times it out over this length, and then divide it by 2 just to make sure we get the triangle. So it's essentially going to be squaring this, because that's this distance, and then dividing it by 2. Alright, so I'm going to say TA2 Alright, so that's TA2, and looking at this here, we see that TA2 and T2 in the same direction, so that means T2 is equal to negative T Alright, so there's our T2. Now let's go ahead and find T1. So normally we look toward the free end because then we don't have to find the reaction at the support, but this case it's going to be easier to look toward the support, because if we didn't, we'd have to analyze this piece of distribution of force, and that's a little bit different because you have a triangle up top and then a square on the bottom. All right, it's not just, you can't really just use quick, simple, similar triangles to do it if you would look that way. But let's look this way, and then we can just do a similar triangles analysis, but we'll also have to find the reaction, but that's not too hard. So let's get a free body diagram happening of section 1. Alright, there we go. So basically the same situation as before, except we got r in the way. If we solve the torques in the x to be 0, we can solve for t. In this case is actually, let's just call it t1. So t1 is equal to r minus t applied in the first piece, ta1. So let's go ahead and find r first of all. So we need to make an overall free body diagram to find r. Alright. Alright, so summing up the torques in the x to be 0, we can see that negative ta2 plus ta1 minus r equals 0, or r is equal to. Alright, so this case we're finding the total load of the total distribution of these triangular pieces. We're not trying to find at a specific point in x. In this case we can just simply say the total torque given by this is just this times length by 2. Alright? So in the first piece, alright, the applied piece in the first piece, that's just t by l, and we're timesing it by a length l by 2. Alright, so there you have it. That's the reaction, T by 6. Alright, now we need to go ahead and find TA1 as a function of distance. Alright, so let's go ahead and do that. So we're going to get a free body diagram of only the first piece. So I guess this isn't exactly a free body diagram. This is essentially the loading that's on a free body diagram. So for a full free body diagram, we can draw in the piece. Add the force. I'm losing it here. T1, and then of course the reaction, which was T by 6. Alright, so the same thing here applies. We can make the ratio of the triangles. So to find what this force here is, right, of course it's being applied like this. We make our triangles. Alright, and this is just a distance x. Alright, pretty straightforward. This full distance here is still L by 2. This is T. And at this point here, it's T by L. Okay, so we can write or we can say alright, so now to find the total force in this triangle, we're timesing it by the area, so that's x. Alright, so then the Newton times meters per meters at this point times the length divided by 2 because it's a triangle. Alright, and now we can say, using equilibrium, that T1 is T over 6. Alright, just using equilibrium of this. I won't get into that. So let's quickly plot this now. It's just a matter of so T1 starts at T by 6. Alright, it goes down quadratically to a value negative T by 12. Alright, I won't go through that at this point to prove it, but I'm going to tell you. And it meets at 0 at approximately 0.4 L. Okay. And now we're going to take equation T2, which develop up here. We'll plot that the rest of the way. And it's going to go like this, quadratically back up to 0. Alright. So I hope this video helped you guys out. And I'll see you in my next torsional bar video.